Yes, thank you. So first of all, I'd like to thank the organizers for the invitation, and also especially I would like to thank Professor Yao, who helped me a lot, not only for me, but also he helped a lot to my family, so which we will never forget. So happy birthday, Professor Yao. So the audience is quite diverted, so I prepared a talk, a simple talk, which starts with some matrices from college level. So nilpotent matrices. What are nilpotent matrices? These are just n by n matrices, which has some power, becomes identity zero. So exists some k, such as this AK is identity zero. Equivalently, this means this matrix has the nth power is just zero, or just the trace of any power of this matrix is zero. And we are working over complex number fields. So this means this matrix is conjugate to some Zhigang blocks. Each Zhigang blocks is of this type. The main diagonal are just zeros, and there are some ones on the upper diagonal. Let me give you just one simple example where n is 2. So you are consider 2 by 2 matrices, which are nilpotent, which means just trace, the trace of this matrix is 0, and also the second power is also 0. So this show you you have two equations for this 4-dimensional vector space. So one is just a linear equation, another is quadratic equation. So you can replace this D by this A. So you just give this, you just got this this singular quadratic surface. And now in this situation, so any nilpotent matrix is conjugate just to one of these two types. First one is just the non-zero, the rank 1 case. And the second one is just rank 0, just 1 point. So you can see also from the picture, this is 0, this original is this just this orbit. This is a single point. And other point are all conjugate. And then we can continue not only for rank 2 case, and then to higher rank, for example, rank 4. In rank 4 case, just 4 by 4 matrices. In this case, you can easily write out these are just Zhigang blocks. For example, this is 4 by 4, and rank 3, and this is 4, 3, 3, 1. You have 2 blocks, and this is rank 2, and so on. And in particular, you can say these are given by partitions of 4. If this is the general phenomena just by Zhigang decomposition, that each conjugate class of nilpotent orbit or nilpotent matrices are just in bijection with partition of this n. Partition we fix first is bigger and then smaller and so on. And whenever you have a partition, you can associate it to some Young diagrams. So Young diagrams means, for example, this is 4. You put 4 blocks on the first line, and then 3 blocks, 3 boxes on the second line, and so on. And then for this, we have some very simple symmetry. Just you do the symmetry along this diagonal, and then you get another partition. Just you count, for example, this is a clone. You have 5 boxes, and then you have first line, you have 5 boxes. So you get another partition of the same number of boxes. So this gives you a symmetry. This is a dual partition. And whenever you have Young diagram, you can consider degenerations. What means degeneration? Means you can move one boxes downward. For example, this red one, you can move to this green one, and so on. So you get from this partition, you get a lower partition. And mathematically, this is just by this inequality. And then you can do this scheme for higher order, for example, SL6 You mean you have 6 boxes and you have a lot of digitalizations, and 7 boxes, and then you have more digitalization. And you can imagine if you have more boxes, then the situation becomes more and more complicated. So what does this mean geometrically for this digitalization? In fact, this means these smaller ones are contained in the closure of the bigger ones. So whenever you have 2 orbit or 2 conjugacy classes, one is contained in the closure of the other if and only if this D can be obtained by digitalizations of Young diagrams from E. So even this is quite easy to prove. Just this is a bigger higher Young diagram, and then you can take a limit of T goes to 0, then you get a lower partition. So this is why this digitalization corresponding to the inclusion order of these nilpotent orbits. And for example, this is SL6, and then you can get the partition of this the 6 partition of 6, and then you can connect by draw a line, which means the orbit of upstairs contains the smaller ones in its closure. And also we can say this diagram is quite symmetric because we have this symmetry by dual partition, so it's really symmetric. But this is only works for type A. And then we would like to consider more not only type A, but all other types. For example, A, B, C, D, and also this is classification of complex simple Lie algebras. So they are classified by A, B, C, D, and also exceptional types, G2, F4, E6, E7, E8. This is first done by Killing. He constructed this ABCD and conjectured the existence of these exceptional types, and then Gartin in his PhD thesis, he really explicitly constructed these exceptional Lie algebras. And then Dinkin comes up with the idea to represent each Lie algebras by the Dinkin diagrams. And also you can say it's quite distinct with this with this Dinkin diagram, ADE and also BCFG, because one is simply list, another is not. And this picture is due to Konglan. I sent to me. This is a picture of the subway station and Kowloon Town in Hong Kong. So you can see also this simply list, you go left, and non-simply list, you go left. And also geometrically, it's quite different. Unfortunately, in my talk, we will not come to this, but in my other talks, it's really different. And now we will consider not only nilpotent matrices in type A, but also in other types. So in general, we fix some simple Lie algebra. You can think about the BCD and so on. And then we say an element is nilpotent. Nilpotent means some linear map is nilpotent. This linear map is just given by this linear map given by the Lie bracket. And whenever you have one element, you can consider the G orbit. And then we say this gives a nilpotent orbit if the element itself is nilpotent. And Kostan showed that if you put all nilpotent elements together, this becomes a nilpotent orbit closure. It's called a nilpotent cone, the biggest one, which is normal and complete intersection. And also nilpotent orbits are classified by partitions in classical types, and also by weighted Dinkin diagrams in exceptional types. And these are general properties of these nilpotent orbit closures. For example, they are not necessarily normal, but they are smooth in codimension 1, which means they are singular. The singularity lies in codimension underneath 2. And also they are stable under the dilation action of C star. So it really looks like a cone. And also the symmetric structure is well behaved with respect to this cyst action. And then there are some works on the normality of the nilpotent orbital closures. And then we can also form this Hans diagram by using the closure inclusions. For example, this biggest one, nilpotent cone, and then you have subregular, subregular, and so on. And then you can imagine the diagram becomes very complicated. If you go to higher rank, for example, this is E6. E6, this is already quite complicated. From E6, this is one orbit, second one, and so on. And then 0 is a 0 orbit. So this continue with this one. And you can say also this diagram is low-more symmetric. In type A, it's really symmetric. You have dual partition. But in E6, already it's not symmetric. In fact, in BCD, it's already non-symmetric. And in fact, what means spatial nilpotent orbit? Spatial means we pick some of these orbits such that the remaining diagram becomes symmetric. So this is spatial. Spatial means we move out some orbits and then the remaining one becomes symmetric. So why is this talk related to this birthday celebration? In fact, this is closely related to Professor Yao's solution to Calabi conjecture in the following simple way. In fact, Bourvil introduced a notion of symplectic singularities by analogy between the smooth part and the singular part. On the smooth part, you have Calabi Yao, which means on the smooth locus, you have a non-vanishing volume form. And as the singular counterpart of this one is called the rational Goldstein singularity, which means on the smooth locus, you have a non-vanishing volume form, which extends to any resolution. And then as a spatial Calabi Yao, we have this hyperkähler. Hyperkähler means you have a smooth vortex with not only with the volume form, but with a symplectic form. So it will become the even dimensional Calabi Yao. And so he asked, what's the counterpart for this hyperkähler in singular setting? And this is a symplectic singularity, which means on the smooth part you have a symplectic form. And also you require this form can be extended to any resolution. So whenever you take a resolution, you pull back the symplectic form, then it extends to a globally well-defined two form. And then the relation with our nilpotent orbit closure is in fact there are two classes of symplectic singularities. Two basic examples. One is a finite quotient, C2n quotient by a finite group. And the other is given by these nilpotent orbit closures. These are important examples of symplectic singularities. Of course, these nilpotent orbits are important in representation theory. So this is one relation with representation theory, which is a Springer correspondence. So this W is a Weyl group. And then Springer established a correspondence between the irreducible representations of the Weyl group and the set of nilpotent orbits and irreducible representation of the fundamental group of this nilpotent orbit. The fundamental group is a finite group. So you have only finite many irreducible representations. And inside the irreducible representations, you have what they call the spatial representation of the Weyl group. This has been defined by Lustig. And also Lustig observed this spatial representation corresponded by Springer correspondence corresponded to some spatial nilpotent orbit with the trivial representation of this fundamental group. And so this is why we define this orbit is spatial. If under the Springer correspondence, this O1 corresponds to a spatial representation. So you cannot say much from the definition. It's really purely representation theoretic definition. And also this is why Lustig wrote in his paper saying that unfortunately the definition of the spatial nilpotent orbits is totally ungeometric. And also they are often regarded as rather mysterious objects. In fact, in my work, we are trying to reveal some geometric perspective for this spatial nilpotent orbits. So what are spatial nilpotent orbits? For example, in SP6, so you have this thinking this Hess diagram, and then this red one is non-spatial, and this blue one are spatial orbits. And also in SO7, so you have also a red one and blue ones. Blue one are spatial orbits, red one are non-spatial. And then you understand why I put these two together in 2 minutes. And also one more example in F4. F4, the thinking diagram, the Hess diagram is really not so nice. But if you just pick spatial ones, then the spatial orbits really form a very nice symmetric Hess diagram. And so, in fact, the spatial one is a maximum subset such that you can form a symmetric Hess diagram. So you just remove the non-symmetric ones. And then we have this Lagrange dual. Lagrange duals, whenever you have a reductive group G, you can construct the Lagrange dual. In fact, in most of the cases, the type will not change. So the type will only change in type S, B, and C. So SP21 corresponds to SO21 plus 1. This is the only case where the Lagrange dual has a different type. And then the motivation of our first work comes from the geometric Lagrange. So geometric Lagrange, you have this Hessian fibration between modular space of Higgs bundles of SLN, and also this modular space of Higgs bundles of PSLN. And then you have this Hessian fibration, and then Hossel and Satas, and then they found these are Lagrangian fibrations. In fact, they proved this is a dual fibration. Dual means for a general fiber on the left-hand side, so it's a torus, and then it's on the right-hand side, it's just this dual torus. And then they made the conjecture that in this case, the E stringent functional are the same. So you have two modular spaces with this Lagrange dual groups. In fact, these two modular spaces have the same stringent functional. And then this has been proved this last year by two groups. And maybe I just jump. This stringent E functional is explicit definition of this. It's a rational function in general. It's not a polynomial. And then now, in our case, we are trying to extend or trying to make the observation to our case. So we need to find a kind of duality between spatial orbits. In fact, this is exactly given by this type B and type C. Type B and type C, they have the same wide group. So for each wide group, a spatial representation of a wide group on the right-hand side, on the left-hand side, so you get some spatial nilpotent orbit in this G, and on the right-hand you get another spatial nilpotent orbit in the Lagrange dual. So in particular, this will give you one bijection between spatial nilpotent orbits in G and also in its G dual or in its Lagrange dual. And the spontaneous show this is order preserving and also dimension preserving. And so the motivation from geometric Lagrange is that what can we say about this orbit and its dual? What's geometry between these two orbits? Because they have the same dimension, they are all also symmetric. And this is SP6 and SO7. So these two SP6 is a Lagrange dual to SO7. And this diagram, so I put I only pick the special ones. And then you say it's really a one-to-one correspondence between these special nilpotent orbits. They have the same dimension. So the question is, if you pick one nilpotent orbit on the left-hand side, and also the corresponding one on the right hand, can we say what can we say about these two orbits? So the naive guess is they should have the same stringent E functionals. So this is the naive guess, and unfortunately, this is not true. So one baby example, for example, in type C, you consider this special nilpotent orbit, and then this is Lagrange dual to this orbit in type B. And for this type B case, you have a critical resolution which resolves the singularity of this orbital closure. So in particular, you can really compute the functional of this one. So in this case, you can show this stringent functional because this is critical resolution. So stringent E functional downstairs is the same as the usual functional upstairs, but this is smooth, so this becomes a polynomial. But on the type C case, you find it's not polynomial. You can really compute this one. You find it's not polynomial. So in particular, you say these two are not the same. So although these two are dual, but they have different stringent E functionals. So how to rescue the situation? In fact, this is given by double cover. In fact, by Kostan, Brzezinski, Kostan, they observed that this type C, this OC has a double cover, which is OA, which is a nilpotent orbit in type A, and this one has a critical resolution given by coordinate boundary of this project space. And then you find out that these two these two have the same stringent E functionals. So in particular, you say the stringent E functional on this OA is the same of this stringent E functional on OB. So in short, the two orbits do not have the same stringent E functional. But but after taking a double cover of one side, then you get the same. So this is our conjecture, joint work with Yongbin Ruan and Wen Yaoxiong. So for dual spatial nilpotent orbit, then you can find some feathered covers, such that after this feathered cover, the two dual space will have the same stringent E functionals. So the main question is which cover will show up, and also these two groups, these two orbits has feathered fundamental groups. And our main theorem is to prove this conjecture for parabolic covers. What means parabolic cover? Means you take a rational homogeneous space, take a coordinate bundle. This is a moment map. Moment map associated to this G action. The image is a nilpotent orbit closure. This is geometrically finite. And then you take the Stein factorization, you get a critical resolution of this XP. And XP is a finite cover of this OP. And then our main theorem says on the counterpart or on the Lagrange dual part, you have also this construction by Springer resolution, Springer maps. And then our theorem says these two called parabolic covers are in fact mirror pattern, which means these two spaces have the same stringent E functionals, and also the degree of this cover is governed by the Lustig's canonical quotient. But for other cases, this conjecture is still widely open. And now in the remaining 5 minutes, so I talk about the second part is about the special pieces. What means special pieces? Means you remove the lower spatial orbits in its closure. Let me give you one example. Maybe it's simple to regard. The blue ones are spatial orbits, and the dark ones or the blank ones are non-spatial. What means spatial piece means you take this closure of this one, so it's the whole diagram downstairs. But then you remove the closures of other spatial ones. So the spatial piece for this one, you get only this one. This is circled by these green lines. And also another spatial piece is like this one. So you get only this one. And so this is just a locally closed subvariety in this Lie algebra. And then in the 80s, Lustig made a conjecture such that the spatial pieces are rationally smooth. Rationally smooth, you may is defined using intersection homology, but you may think about it's quite close to be smooth. For example, if it's a finite quotient of a smooth variety, then it's rationally smooth. And then this has been checked by Shoji in F4, and also by Ben-Yong Spartan test in EN case, or by Craft and Pochese for classic types. And then Lustig also showed what happens for this Lagrange dual orbits. And then he showed the dimension of this G equivalent cohomology are the same. And in the same paper, Lustig proposed the following conjecture, which will explain why it's rationally smooth. So he said if this spatial piece is a quotient of a smooth variety by our finite group. So this is his conjecture. This has been done for classic types by Craft and Pochese. And in 2009, Archer and Sage, they proposed a candidate of this smooth variety by using the linear and Kavarnikov theory of purpose coherent shifts. But the smoothness of this candidate is quite difficult to check. So our main theorem of the second work with Yudo, Levy, and Summers, which says we consider a transverse slice of the spatial piece. And then we can really describe the transverse slice. The transverse slice is very simple. It's just a quotient of a smooth variety by our finite group. So we cannot prove globally it's a quotient of smooth variety by a finite group. But if you take a transverse slice, it's just a quotient of smooth variety by a finite group. The corollary we show spatial piece is rationally smooth. So this gives another proof of Lustig's conjecture in the 81s. And also they are normal. This is a new result. Before us, this cannot be proven for E7 and E8. Just 1 minute for the proof. In fact, we divided to several steps. The first one is for two orbits case. So if the piece consists of two orbits, then this has been done by our previous work in 2017. And then the main contribution in this work is for higher orbits. For example, if you have a spatial piece which consists of three orbits, this is G2 case. This is E7 case. And in this case, we show transverse slice of this one is just the isomorphic to this one. And also this one is isomorphic to this one. And also the bigger one spatial piece of this F4 case. So you have this big piece. This big piece, then we show this is we show this is also a quotient by S4. S4 this each correspond to the partition of this 4. This is stabilizer of each orbit. And the biggest spatial piece is in E8. So in E8 you have this 8-dimensional spatial piece like this one. Then we prove this is isomorphic to this quotient of this C8 quotient by S5. So my time is up. So thank you.
Questions?
I was wondering if your computation of string E functional from the first part of your talk uses non-Archimedean integration or not?
Yeah, yeah. We did try this. Yeah, I think. Yeah. This is the method proved by the first group. So, yeah, we don't know. We don't know how to use this. So the main problem is try to find a nice resolution and to do this one. Yeah, it's a good question, but we don't know how to show this.
Any more questions? Only one, because we don't have time. Okay, if not, let's thank Baohua again.
Thank you.
Next talk starts now. Okay, it's my pleasure to introduce Professor Vadim Vologodsky of Higher School of Economics and Princeton University, who is going to talk about crystalline periodic cyclic homology.
All right, thank you for having me here. So the title of my talk may look scary, but I see some experts in the room, and I want to tell them that you made a mistake by coming to my lecture. So this talk is not for you. So everything original that I'm going to say is a joint work with my former student, and Alexander Petrov. And it's inspired by beautiful lectures of Maxim Kontsevich from 2005. And in particular, I hope at the very end, I will show you a proof of some of his conjectures. So here is the plan of my talk. The first 3 items is a review of results from 70s. The second 3 items contain some original results. I would like to start with actually the last item. So what it is all good for? So what does it buy you? Well, one thing that I learned from Professor Yao when I was a graduate student at Harvard was his joint work with Leon, where they proved the integrality of the mirror. So together with Kontsevich and Schwarz, we developed their ideas further, and in particular, we proved the integrality of instanton numbers in B-mode. So the main idea is to use the Frobenius action on the Durham homology of one-dimensional family, of one parameter family of algebraic varieties over periodic numbers. So this S is my base, which is in this case just affine line. And I have a smooth family, X over S, and the Frobenius is a map you see on this slide, which has a property that it's compatible with the Gauss-Manning connection. And just the very existence of this map imposes can be used to study integrality properties of Gauss-Manning connection. The main idea is the following, that if you take any homology class S and apply Frobenius to this class, the covariant derivative of phi of S must be divisible by P. So if you apply Frobenius n times, then it must be divisible, the covariant derivative must be divisible by P to the n. In particular, if section S you start with has the property that the limit exists, this limit must be flat, which means that you can construct some flat sections of this homology, which has periodic, whose Fourier series expansion has periodic integral coefficients. That's the main idea. Okay. So, however, well, there are other areas of mathematics where flat bundles appear, and in particular, one has Gauss-Manin connection on periodic cyclic homology of any associative algebra, or more generally differential graded algebra, and more generally differential graded category. For example, for Kaya category. And so what we want to do is to study the integrality properties of this connection, Gauss-Manin connection, by introducing Frobenius. And well, I want to start with a kind of baby example. So if I have a commutative algebra over in characteristic P, over a field of P elements, then the map that takes A to the pth power is an algebra endomorphism. So it takes sum to sum, product to product. If A is merely an associative algebra, this is not true. However, the difference, the failure of this additivity, right? A plus B to the pth power minus A to the pth power. Oh, sorry, there is a misprint. Minus B to the pth power is an element of the subspace of A generated by all commutators. This would be a formal consequence of the first item, commutative case, if this A comma A bracket would mean the ideal generated by all commutators. So this is slightly non-trivial, and I learned it first from Kaledin a long time ago. But well, if this is a very good problem for your first year undergraduate algebra class, right? So that's a very nice exercise. Again, there is a minus sign there, minus B to the pth power. Okay. So what I want to do, so that means that we have a well-defined map from the vector space A modulo the commutator of A with itself to itself that takes any element A to its pth power. And so what I want to do something similar, but now over periodic integers, right? So right. So I want to start with a yeah. Go back. Yeah. So to start my talk proper by recalling for you what de Rham homology, algebraic de Rham homology is. So this were introduced by Alexander Grothendieck in his letter to Michael Atiyah in 1933. So here you see the picture of them discussing algebraic de Rham homology. And well, what you do if you haven't, say, in a fine algebraic variety, you just take polynomial differential forms on X, closed differential forms, and mod it out by, take the quotient by the subspace of exact forms. That's the homology group. And so if X, so you can also interpret it as a homology of de Rham complex, and if X is not affine, then you have to use sheaf theory to define it, because otherwise you can have very few differential forms, and the answer is not reasonable. So that's how you define it in general. You look at sheaf homology of X with coefficients in the de Rham complex. And well, so if X is affine, then the two constructions agree. And also you have Maya-Vittori sequence for the de Rham homology. And this can be used to reduce computation to the phi case. Okay, so yeah. So I need time here. No. Okay. Good. Very good. So I started at 2:30, I guess, right? Okay, good. So what are the well? So in this definition I gave here again, I secretly there is a base ring or base field we are working over. So X is a smooth algebraic variety over something, right? I can consider algebraic de Rham homology of complex varieties, and then there is a fundamental theorem, beautiful theorem of Grothendieck, that says that algebraic de Rham homology of X is agrees with the de Rham homology of underlying smooth manifold. So that means that every differential form, every homology class on X can be represented by a polynomial differential form, which is a really surprising result. Right. So, but you can also study algebraic de Rham homology over various fields or rings like Fp, Z over Zp. So if you have an algebraic variety given by equations with integer coefficients, you get some integral lattice in complex de Rham homology, it's not the better lattice, it's a different lattice. So it's very interesting. Here is an example, which is, you might find it disappointing. So if you take a simplest algebraic variety over a field of p elements, A1, a fine line, then you see that de Rham differential of p power of x is 0. So it's an element, it's a class in H0. And so it's H0 is infinite dimensional. And also you see that differential form x to the p minus first power times dx is not exact. So you have plenty of classes in degree 0 and in degree 1. So homology groups are infinite dimensional and also not A1 homotopy invariant. Okay, situation is better if x is projective. It's fine. Okay, so the next thing I want to tell you about is crystalline homology. This was discovered by Alexander Grothendieck and developed further by Pierre Berthelot in his thesis. And the key idea, well, the consequence of their construction is the following. So take a smooth projective variety over periodic integers, right? So you given by some equations with periodic coefficients. Then its de Rham homology functorially depends on the reduction of my variety modulo P. So here is an example. Take these two projective surfaces over Zp. There is no significance in the choice of these coefficients except that they're congruent modulo P. And the claim is that their de Rham homology is isomorphic. Okay, so right. So what Grothendieck actually did, he constructed a functor that takes a smooth variety, not necessarily projective, over a field of p elements, and assigns to it a cochain complex that computes crystalline homology. It's a complex of Zp modules. So we start with an object defined over Fp, and output is a complex of Zp modules. Well, it's defined up to quasi-isomorphism, but at least you have homology groups which are Zp modules. And it has the following property that if you reduce this complex modulo P, you recover the de Rham homology. And if you on the other hand, if you have x, which is over Fp, and you are given a smooth lift of this x over z mod p squared z, over Zp. So, for example, you have a hypersurface given by some equation with coefficients in Fp, and then you lift coefficients arbitrary to just elements in Z integers. So that's going to be a smooth lift. And then it says that the rank homology of this smooth lift compares with crystalline homology, at least after P completion. But if X is projective, then you don't need to take completion. It's already finitely generated ZP module, it's automatically complete. So that's the idea. And so I explained, this is the first 3 items of my plan. And so now I want to tell, oh no, this is 2. So now I want to tell you about periodic cyclic homology. Sorry. First, I need to tell you about the crystalline Frobenius. So, well, every algebraic variety over a field of P elements in characteristic P has a fundamental additional symmetry, Frobenius. So it's just takes, if your variety is given by equations with coefficients in P, you just raise every coordinate to the pth power. It preserves the system. So by functionality, it gives you an endomorphism of crystalline homology, which is, in fact, it's an isomorphism after inverting P. So for the applications, for example, for the application that I sketched at the very beginning of my talk, this is not quite enough. So you want to know, you want to measure the failure of this Frobenius endomorphism to be isomorphism integral. So I said that it's only isomorphism rational. So, and here is a more precise statement, which was kind of implicit in a major paper from 1973, and well, it was since then it was kind of known to experts and made explicit by August quite recently. So the statement is the following: suppose you have a smooth, proper scheme over ZP, again projective, and suppose that its dimension is less than P. Then the claim is that the crystalline Frobenius, which is an endomorphism of the de Rham homology of this scheme, right? It actually factors through a larger. So here you see kind of larger complex, right? You add some denominators. And so it's the claim is that the Frobenius, the source of the Frobenius map, is in fact can be made larger, and then it's an isomorphism. So, well, it just says that equivalently, it says that the Frobenius is divisible by P to the I on the ith term of the Hodge filtration, and no more. So equivalently, it can be formulated in a beautiful way as follows. So you look at the de Rham complex where the differential is P times the usual de Rham differential. And the claim is that it's canonically isomorphic to the de Rham complex, usual de Rham complex. So take this isomorphism and reduce it modulo P. Then you get something interesting. One differential becomes 0, the other one isn't. It's usual de Rham differential, right? So okay, so that's kind of okay, sorry. That's the commutative story. Now I want to tell you something about non-commutative. Well, Hochschild homology. So if I have any associative algebra, Hochschild homology of A is defined as follows. You form first A. You consider the A as a bimodule over itself, right? As a module over A tensor, the opposite algebra. And then you take the derived tensor product of A with itself, right? Well, why not? So what does it good for? So, well, this is for perspective of my talk. It's motivated by this result of Hochschild, Constant, and Rosenberg that says that if X is a smooth affine variety, then you recover differential forms. Now, the space of differential forms in differential geometry has a lot of structure. You have action of vector fields by Lie derivatives, by substitution. You have the Ram differential, and you have the Cartani relation. And it turns out that everything is present on this non-commutative board. So you can replace differential forms by Hochschild homology, and you get all this structure, except for the multiplication ring structure. So the most interesting piece of structure is the de Rham differential. So remember that H Hochschild homology in degree m is an analog of differential form of degree m. So the analog of the de Rham differential is this operator, which I depicted as B bar. So sorry. So this operator was discovered by first by Reinhardt, then it was forgotten, and then rediscovered by Alan Kohn. And well, its construction uses an explicit chain model for Hochschild homology. So it's this de Rham differential B bar is given at the end by some explicit formula. So you write some canonical, flat resolution, pre-resolution for A as a bimodule, and then you use it to compute these chores. So it's explicitly it's given by some complex form by tensor powers of A. These rather complicated differentials, and so then the Reinhardt-Kohn construction actually leaves the de Rham differential on the chain level. And that's very important. What follows, so it's they defined for any associative algebra a map from m tensor power to m plus first tensor power that has which looks first of all it commutes with the Hochschild differential total, and secondly it squares to zero. Here is an explicit formula in some small degrees. I want to write down formula in general. So, and once you have de Rham differential, you can look at non-commutative de Rham homology. So what you do, you look at the so you have here Hochschild chain complex, and here you put the de Rham differential. You look at this bi-complex. It's really a bi-complex because of the delta commutes with B. And then you take the product totalization of this complex, which can be conveniently organized as, you can enjoin a formal variable U of degree 2 and introduce a differential, Hochschild differential plus U times B, then it's differential of degree 1, and you take homology. It's called periodic cyclic homology. And this should be thought as a non-commutative version of the de Rham homology. So the basic properties are the following. So first of all, if A is commutative, then HP, the periodic cyclic homology, has an algebra structure. And it's a module over Laurent polynomials in one variable, degree of U is 2 again. So, and if X is smooth affine variety, then this periodic cyclic homology has a canonical filtration indexed by integers whose associate graded is de Rham homology. Okay? So, lastly, so periodic cyclic homology can be defined not only for algebra, but also for differential graded algebra and even for category. Okay? So now it comes to the some regional results. So what I want to have is we are interested in periodic cyclic homology of algebras over FP. First, I want to have its crystalline lift. So I claim that there is a construction that assigns to any algebra over Fp functorially a complex of ZP modules, which has properties similar to crystalline homology. First of all, if you reduce this complex modulo P, then you get periodic cyclic homology of A. And if your algebra A admits a Peterson Phi lift over ZP, then you recover periodic cyclic homology of that lift, at least after P completion. So in particular, you see that this right-hand side functorially depends on the reduction of A tilde modulo P. Okay, that's okay. So well, I'll sketch explain an idea of this construction. So the idea is crazy. So if you have any algebra over a field of P elements, you can consider it as an algebra over Z, over periodic integers. So, and then you can look at its periodic cyclic homology. It looks completely stupid, right? Because periodic cyclic homology is formed by tensor powers of your algebra. And if you have a vector space over Fp, then it doesn't matter whether you take the tensor product over Z or over Fp, you get the same result. However, it's not true if you take the derived tensor. And that's what you are supposed to do when you work with periodic cyclic homology of an algebra which is not flat over your ring. So, we'll have a complete example in a second. But what I want to point out is that so this HP. So again, let's take A over Fp and we look at its periodic cyclic homology over Zp. And by general nonsense, it's an algebra over the periodic cyclic homology of Fp over Zp. And the key step of the construction is producing an algebra map from HP of Fp over Zp to HP of Zp over Zp. So there is an obvious map in the opposite direction, right? Because Zp maps to Fp. But the claim is that there is a section. That's a miracle, right? So once you have this, you just form a tensor product. You start with you take an algebra over Fp, you compute its periodic cyclic homology over Zp, and then it's not a correct answer, but you correct it by forming this tensor product. And this map is needed to really to form this tensor, right? So just one example. So here is a computation of HP of Fp over Zp. So it can be identified with a power series, divided power series, right, in xn over n factorial with periodic integer coefficients, modeled out by single relation that x is equal to p. So this is not quite enough. This at least gives a map from periodic cyclic homology of Fp over Zp to Zp by sending x to p. This is not quite enough. It's what we need is an algebra morphism, which is, well, differential graded algebra morphism or infinity algebra morphism. So the actual construction is more complicated. I will skip it. But what I want to say is just maybe the last slide. So there is a comparison with periodic topological periodic cyclic homology. But what I want to say now is the kind of the last result is state the last result, which is so remember that we want to have a crystalline periodic cyclic homology of algebras over Fp, and we also want to have Frobenius. So the claim is that by using some comparison with topological periodic cyclic homology, so if I start with any smooth proper DG algebra over Zp, then so there is a canonical endomorphism, well, of rational vector spaces. So you take just HP of your algebra, tensor it with rational numbers. And as in the commutative case, as this analog of, there is an analog of this more precise result by Mazur and August. Remember that the result says that the de Rham complex with differential P times D is quasi-isomorphic to the de Rham complex with differential D. And here is a non-commutative version of this result, which was conjectured some time ago by, in 2005 by Maxim Kontsevich, and well, modulo P, it was proven by Kaledin and Matthew, and Achille Matthew. So it says that something similar is true over HP. Okay, I'd like to conclude by wishing happy birthday to Professor Yao. Thank you very much.
Questions?
So the exterior derivative of the drum coming from this combination of Frobenius and this other operator.
Right.
Okay.
You should try the supercommutative case. Supercommutative case, which is a special case of your non-commutative case.
Well, I haven't tried it, so, but yeah, probably it's a
it's
possible direction.
mystery. I don't know if it is related, but it's always mystery to define super Cha homology theory. Does it communicate? I mean, can you say anything about Cha homology? No,
I don't know.
not. Questions? If not, let's thank Vadim again. A coffee break now. Next talk is at 3:20 in 20 minutes.
Manifold fitting, an invitation to statistics. Let's welcome.
All right. Thank you very much for the introductions, and it was my great honor to be here. So I'm going to talk about the stuff that I started doing since 2014 when I came back to Singapore. So this is actually has something to do with my previous work, but today I'm just going to only give a very high review about the things that I've been collaborating with Prof. Yao and also my students and postdocs and so on. So for a very long time, that I would think that at least 10 years before I graduated, also 10 years after that, then people have been using linear subspaces trying to approximate high-dimensional data. Right, and this, I mean, that's why usually I will actually say that linearity was actually deeply rooted in statistics, also data sciences. Then when actually it comes to curvatures, when you have a lot of data and with a lot of dimensions, and for example, we have a p dimension of different variables, and that not every single variable or not every single directions of these features are actually important. So people have been doing, let's say, variable selections, trying to pick up some of them out of, let's say, p different variables. So this has been done at least for actually 20 years. So the thing I want actually to do is trying to do different things, meaning that I'm actually trying to learn a manifold behind a high dimensional data, because I assume that there's actually lower dimensional manifold behind a high dimensional data without actually cutting off these sort of variables. So this is joint work with a few authors, and also My talk today is actually going to be based on the 2 PNS papers that we have been recently published, with one actually still being revised as well. So the motivations, because I only have, like say 25 or 30 minutes, I just wanted to mention things like, okay, if we have high dimension data, this is just the toy problems. I'm actually going to show you some real problems that we have been working on. So toy problem says that if you have a bunch of data, let's say this these kind of points lying on the Swiss row, and if you want to just simply wanted to do classification or actually clusterings, so what people have been doing basically is that they flatten the whole Swiss row, doing dimension reduction, transform the data from 3 dimensions to 2 dimensions. Then you actually arriving on a piece of paper in 2-dimensional planes. And then they can actually perform clusterings, also, for example, classifications. But if you flatten the whole thing, then you don't actually have the Swiss row, meaning that for example, if I'm actually sitting right here at the red point, you have to go through the whole Swiss row to reach to the blue point. So using the Euclidean distance or using actually some kind of embeddings are not going to help you with the actual geometry of this data set behind it. So this is why we actually wanted to do this. For me, for manifold fitting, I wanted actually to fit a manifold. In this case, the Swiss row behind the high dimension data. In this case, it's still going to be low dimensions. Right. Later on, I'm going to talk about single cell project that we really have to deal with, let's say 15K to 40K dimensional data sets. Then we actually need to fitting a manifold with less than dimension 10. All right. So there are at least 2 ways you can actually think of, for example, data actually lie exactly on a manifold. For example, you have, earthquake data. These are the locations people usually pick up, right? For example, you will see that these are the blue dots are actually, lying on a piece of paper, but this is actually the location for every single earthquake. So if you think about the Earth is just the S2 or ellipsoid that you were seeing, that the 3-dimensional vectors actually lie on that S2s. So dealing with the analysis, you actually have to, take care of, the geometry behind, meaning that every single point needs to lie on the S2. So every single methods, if ideally you wanted to analyze them, you have to take care of the constraint that the x squared, for example, plus y squared plus z squared equal to the radius of the Earth, that's all. So for example, I want to actually to fit a flow that actually lying on exactly on the S2s. And for example, the flow is trying to track down the trend of this earthquake. So this is basically we have actually developing myself actually with some other folks from Switzerland. We have been doing something called a principal flow, which is very going to be introduced very, very shortly. The second scenario is that you are basically dealing with matrix, let's say M by P matrix or P by P matrix. I don't really care, but because of this nonlinear constraints, then they force the data sets, for example, the matrix or vectors, lie exactly on a manifold. So it's really up to you to actually treat the vector as a vector, or treat the matrix as a matrix, or actually treat the vector as a point lying on the lower dimensional manifold. This is a very simple example. If we're dealing with, let's say 3 by 3 covariance matrix, right? It's just a covariance matrix. It's PSD, so it's 9-dimensional. That's how people actually treat the matrix in computer science. So if I let the P3 become the space of all PSD, so basically we can actually reduce the P3 to R6, because these guys are D12, D21 are actually the equal, and D23 and D32 are also equals. But R6 is still too big. It's too big. So basically, the P3 is convex, but not linear. For example, if I have one D1, the other is D2, the 2 matrix, any linear combinations might not actually in this P3. So you actually have to actually embed them on a cone, for example, living in R4. So which means that we have to develop things that actually can take care of these data points lying on the cones. For example, we want actually to extend a PCA, which was usually defined in the Euclidean space on the PCAs actually, defined on the manifold. So this is the first things we actually come up with around 2014 is actually called a principal flow. I want to fit a flow, track down the variation of these data sets that, my goal is very simple. I just wanted to get a flow. Actually, every point on the flow computed from the data sets, its tangent vector of the flow will be very close to the, let's say, the first eigenvector that you calculate from the local covariance matrix, meaning that the flow track down the second order covariance matrix globally. Now the question is, can you actually get a global flow or not? So if you think about the ping pong ball right here, then you can actually compute the vector field from these data sets. The data sets actually lie on the manifold. Then you want to get a flow such that you start from the first mean, for example. This is just a very simple illustration of what behavior that I actually expect the flow to have. So I actually move a little bit. This can be on the tangent space, follow from the first eigenvectors that I compute from the local covariance matrix. Then this is the flow, the gamma I want. Then I hope that at every tangent vector, at every point on the gamma, its tangent vector is very close to the first eigenvector computed from the local covariance matrix. For example, this arrow is actually pointing to that sort of the directions, and this error was computed from the data set that actually captured from this local covariance matrix, meaning that we have to actually map the data to the tangent space, not just compute them using the Euclidean PCA stuff. All right. So the technical point of this definition, for example, of the flow is that we basically want the tangent vector of the gammas it stays very close with the vector field, which is called W here, at every single gammas. So if someone can solve this integral problem, meaning that we just wanted to solve this integrations along the whole gamma, because gamma in this case is one-dimensional. So you can always, parameterize the gammas. So in that sense, we can actually get the flows. And the flow, by the way, is supposed to be lying exactly on the manifold. The flow is not going to go inside or outside of the manifold, traveling around the whole Euclidean space. So this is what I call the principal flow. And so if the manifold actually collapse to the Euclidean space, if we have the huge neighborhood to compute the covariance matrix, then we can actually prove that under some conditions that the flow is going to reduce to the ordinary PCA in the Euclidean space if the manifold collapse to the Euclidean space. So this when we actually try to naming this thing, then I would just find out that Charlie Hisley has already named this whole thing as the principal curve, because we wanted to name this as the principal curve. But his work is basically trying to trace down a flow from the data sets, that every single data set, or also the flows actually living in the whole Euclidean space. That doesn't have to be on the manifold. So basically my flow, or our flow, is just a manifold version extensions of their flows. All right. So, so actually, back to our already 8 years ago, when I went back to Singapore, I was thinking, okay, maybe I should extend the principal flow idea to a let's say 2-dimensional or 3-dimensional or multi-dimensional submanifold things. Meaning that if I give you a bunch of data sets, right? So, in addition to get a flow, maybe I want to get a surface that on every point on the surface, which to be determined, it's actually tangent planes. Now I don't have a tangent vector. I'm actually going to deal with a submanifold. So it's tangent plane, and also should be very close to the space that's spanned by the local, let's say, k eigenvectors. So we're now dealing with, in this case, the angles between the two hyperplanes. So I hope that at every point beyond this on the submanifold, that I hope that these two planes can actually parallelize at least. So if someone can solve this integral problems for every point on the submanifold, then this is going to be wonderful, because in that sense, I can get a global submanifold, which I call the principal submanifold. It actually turns out that it's not that easy to actually get a global principal flow. Sorry, the global principal submanifold. So we ended up getting a local version of the principal submanifold in the sense that we have to parameterize the whole submanifold to its tangent space and actually using polar coordinates, meaning that the log map is essentially local. Right. So to parameterize a submanifold is not as easy as parameterize a one-dimensional curve. Right. So now this is the submanifold business. Then if someone can actually get, let's say fit 2 different principal submanifold for 2 different kinds of data, then maybe a very nice boundary that we can actually draw, which try to classify the 2 data sets. So this is not a picture of a bird. This is the picture that I actually fit the 2 flows or 2 submanifold from 2 different kinds of data. Then once I've done that, the whole curve, which is in blue here, is also in red here, representing the principal submanifold from the 2 data sets. So for me, if I wanted to do some fancy things to classify the 2 data sets, I don't have to a boundary which classify the two data sets. I only have to do a boundaries which separates the two principal submanifold. This is ideas. So we actually call this as the principal boundary lying on a manifold, which was on this work was done like 4 years ago or something, like five years ago, which we call this a principal boundary things. Now, everything so far I've actually mentioned is that the data lies on a manifold. You basically know the geometries. Basically, you know how to embed data onto a manifold. And then you do operations on such kind of manifold where you do know the geometries. This is already very advanced to most of the data science techniques. A few years back, I would say 4 years back, I was thinking, if I don't know the manifold, then can we actually estimate the manifold? This is a central problem which bothers me at least for 5 years so far. So I want to use the rest of the time actually talk about the manifold fittings. By the way, I just wanted to mention that a few years back, I actually realized that the principal submanifold business I've been doing is actually a empirical way of actually decompose some kind of spaces, and this has something to do with the SYZ conjectures, at least from my point of view. Due to the time limitations, I just wanted to move to a manifold fittings. So as I said, I actually keep giving talks at different universities, Harvard, Cambridge, all kinds of places, Duke, Johns Hopkins, and Berkeley's. And until someday, somebody emailed me and he said, maybe I should do some very extremely apply work so that everybody can actually use my framework. So this actually motivated my next research. So I've been collecting data with my group members. We have been collecting data. These are the single cell data. This is not toy data. This is a real business. So people scan the single cells, and we're actually dealing with 15 to say 40K cell dimensions data. So we've got at least 1,000 of samples. We can actually deal with up to 250,000 samples. So what do I mean by this? These are the data sets you actually have. These are the classes people spend time and money to actually classify these things. What I want to do is actually trying to learn a manifold behind these data. Then I hope that after this whole manifold fitting, maybe it will actually become much easier for people to actually classify things. I'm going to show you some results, okay? So this has something to do with a very old problem called geometric weighting problems. So for me, that I will actually deal with, let's say, y is the data, x is the some vectors lying on a manifold, which I have to estimate it. We're given a measure. If you put some noise on it, you basically lift the x to the ambient space. So y is my data. I observe the y. I want to estimate the manifold, and also sort of bound to the distances. Of course, someone can write some papers based on this. Now, there's a few different things I wanted to mention here every time I give this talk. So this is the manifold in dash, and the points in black are the datas. For most of the methods, even some methods called manifold fitting, manifold learning, which was basically from the 1990s to the early 2010. These people basically try to push these things into lower dimensional subspaces, which I call the embeddings. Once they are done with the embeddings, they live there. You can't really go back to the original ambient space. You are finished. So what I wanted to do is push all these points to the manifold in the original space, meaning that the red dots right there I'm pointing to are very close, hopefully, to the underlying manifold. So this is called denoising, basically. I'm doing everything in its original space where the data was measured. If the P is 200, if the P is 40K, I don't care, but it's going to be inside the original space. All right. So if these red dots are going to be very close to the manifold, which I can prove, then we can actually fit a smooth manifold no matter what. And then, so this has been some developments. So ever since 2012, these are the real manifold fitting literatures, starting from 2012. Larry Walsman, also Christian University, has started this kind of work. I had a paper with Larry. I didn't know he actually started to work on this almost like 10 years ago, and also 4 years later, Pfefferman started to work on this with his postdocs. So we've basically improved their 16 and 18 papers using one of our methods, which was in 2019, I think. Then later on, we have some long papers, and I don't have the time to actually discuss every single entry of these literatures. Let me just move on. So this is the framework. So we've got data. So the I goes from 1 to n here. So xi lies on a manifold, which we don't really know. So if you have a convolutions, basically yi is the measure of the x on the manifold with the noise density functions. So you observe the yi, you have n of these guys. So your job, or my job, is trying to push the yi's in its original space so that they can stay very close, hopefully, to the underlying manifold. This is called a manifold learning. I do not reduce the dimension of the yi's. I do not do variable selections. Yi is still going to be RD. D is the dimension of the ambient space. All right. So the manifold is assumed to have the dimension small d. That's all. All right. So the idea of my 2019 paper is that you actually look around and you actually try to estimate the covariance matrix. Sorry, you try to estimate the tangent spaces. But this was not as good as actually try to directly work with the normal space. If I'm sitting here, y here, right? Y, yj are the data points. So Pfefferman basically used 2 steps to project the y's to the manifold as close as possible. So he has to somehow go through the estimating the tangent space, which is always going to be subject to dimension, let's say P or capital D of the ambient space. What I wanted to do is directly work with the normal spaces, meaning that even if you can actually estimate the projection matrix, this is where you are going to arrive, which has this bias. So one thing to think of this other box is that if you can actually get any arbitrary point as close as this manifold, for example, in this picture is a B here, I don't want to actually estimate the tangent space, which is in dash. I just want to directly write down here using the normal space. So this will give me much smaller bias. Just one-time shot, you can actually get to the manifold. So this is essentially our 2019 paper with my postdoc. So 2022, during the pandemic, and Pfefferman has another paper which try to improve the quality of their projections. So if the noise level is sigma, they claim they can do the manifold fitting actually reaching to the sigma square distances in terms of Haussler. So our long papers actually also can achieve this kind of things. So the idea of actually doing this now is not we do not look around here using a Euclidean board trying to push this red dot to the manifold. No, we're going to do 2 steps. One is that we want to push this red dot a bit further, closer to the manifold. For example, in this case is the blues, so that we can guarantee the blue dot has, let's say, O sigma at least distance from the underlying manifold. Well, it actually turns out that you can construct a cylinders which actually will give you a direction to push the blue dot further in the sense that the blue dot can be pushed furthermore, reaching to the green dots. The green dots will lie at least the sigma square distances. If the sigma is actually small, then this is going to be a very, very nice result. So this is our 2022 paper, and eventually we're going to actually combine this manifold techniques with some machine learning techniques. So how many minutes I have? Okay, cool. So the recent PNS papers basically deal with the so-called game theory GANs. I actually didn't know too much about the scan, but I organized a conference at Harvard 1 year ago with the help of Yao, and David Donohue told me that maybe I should combine with the manifold fitting with the scan. So what's going to happen? So this is actually a very interesting idea. In the beginning, I didn't even realize this is actually going to work because I don't know too much about GAN. But let me explain what I know about the GAN. So basically, you get a you've got a low dimensional space which is called feature space. You are trying to learn a map between the z and y. So y is in high dimensions. Let's say that the dimension was capital D. Let's say. right? So you've got to train two generators. One generator is called the GZ here, trying to map this data from the lower dimensions to the Ys to the high dimensions. Then you actually the one generator is actually pull the thing back. There's also another two generators. Sorry, there's another two discriminators trying to discriminate the fake data and also the true data. So what do I mean by fake data? So if I have the Z here, which can be any noise, then I can generate some actually in the fake data, which is called Y tutor here. So Y tutor is not a data you actually observe, it's the fake data I generated. So the discriminator need to have a job to differentiate the Y tutor and also the Ys. Right, and also there's another discriminator called GZ here, which is going to be differentiate the Z tutor with the Z here. Now, well, this is again we can train it. Supposedly, the machine learning people is actually going to train them, right? Fine. If you are patient, if you have a lot of data, yes, you can train them. But what I wanted to do is actually before I pass this high dimensional data to the discriminators, I want to do a manifold fitting. The reason is that I think that if I push the Ys in a high dimension, in the ambient space, so that they can lie much closer to the underlying manifold, maybe it's a good thing for dy to differentiate. So the system is actually in the one way try to mimic the true data to fool the system of this dy and dz's. At the same time, the dy the dz wants to do a better job to differentiate the two guys. So I believe that the FM putting between the y and dz dy here is going to be helpful. Now, if I can still train this the gz here, then this can be a manifold estimators, or I can just do a fitting on the resulting generators. So this is very similar as the surgery things that Yao has mentioned in his pure math work. So both of these estimators can be used as a manifold estimators. So this is basically the idea of our PNAS paper, that the core idea is actually behind the long papers in 2022. Of course, in terms of implementation, so somebody is going to worry about the different biases and trying to train them use the loss function. Thank you. And one thing I want to mention is that we can also, when we actually get the manifold, then we can do interpolations, meaning that we can bring in new sites of data, these data which has not been observed. So the one thing we can do is that we can actually transform these high dimensional data YIs back to the lower dimensional case. Then we do the interpolation there. Then we transform them back to the GZ head. So this is called interpolations. I just wanted to ignore these toy problems and just wanted to give you the real stuff that I think was some the effort. So this data is one row, the first row of the previous 25 data set, single cells. It has dimension, let's say, 3,000 and samples, let's say 700. It came from the stem cell from the mouth, and it has 3 different classes. Now, we will pretend we don't know the class. Well, you will see that, so what? I mean, we've already got deep learning, all kinds of things. Fine. This is a 2-dimensional representation of the data set before using manifold fitting. You can see that they are mixture. They are actually sort of, the mixture together, right? By the way, the capital D here is 3,000. So we can view them only in 2 or 3 dimensions. People can say, okay, let's just use deep learning. So we tune the parameter to hell so we can get 95%. Fine. One thing I want to show you, the take-home message here is that I'm not going to use deep learning. I'm just going to fit this data set, giving you back the same M by P matrix, meaning that I'm going to give you 700 multiply, let's say, 3,000 dimensional matrix back. Then I try to visualize them. This is the result. You can see that they've already been aligned very well, separated very well. So now, do I still have to use the deep learning? Yes, of course, you can use it. But any high school students who knows how to do the k-mean clusterings can do this very well, getting, let's say, 0% Well, you will say, okay, this might be just one of the coincidence. Well, last year I thought maybe yes, this is just I'm too lucky to do that. We've been actually trying to check the manifold fitting on 25 single cell data sets. These are again data sets coming from the last 10 to 15 years. People published the single cells on the Nature Science Cells. These are the results. So my student told me that this SCDHA is one of the best, let's say, clustering things that people using in the RNA single cell. So we're just going to compare with them. So you can see that we have, on average, before and after the fitting, I can improve the accuracies up to, let's say, 25%. This is a very impressive results. And again, this is we are actually using this ARI stuff, which is the random index. So if we simply compare with the accuracies, we can actually improve 35% on average over the 25 different data sets. So this is the second the PNAS application paper that I'm going to share with you guys. Now to push forward that we actually have been collecting data sets from the real experiment that people spend $1 million on it. So this is going to be 60 data sets. We have a data bank, which is around the 80s, but this is going to be the 60 data sets. So we're proposing a thing called the SCAMF. So single cell analysis with manifold fitting. This is the pipelines. So we compare with this pipelines with the 8 dominant pipelines in single cell analysis over the 25 data sets. Then you can see that we're still actually, not beating like uniformly, but on average, we are doing a very good job, meaning that something must be done correctly. Otherwise, we won't be having this kind of, performance compared to the 8 dominance pipelines. So our goal is trying to finish the analysis for, let's say, 250,000 cells where, dimensions, let's say 40,000, within, let's say, 20 minutes. This is the standard, the time spent for most of these 8 dominant, the pipelines. So this is the result. And I think since I only have limited time, which is one minute. Okay, so I think I'm going to stop here. But because I grew up from China, so I want to say something using Mandarin Chinese to show some respect to my countrymen. 所以这一次来这个北京非常荣幸参加这个邱振龙教授的这个75岁生日的这个派对或者 conference。然后我觉得邱振龙教授邱先生比我懂太多的这个数学。然后呢，我应该比他懂稍微一点点这个统计的东西，但是呢，显然我跟他应该是不同时代的这个人，但是我觉得我跟他之间有一个共同点，就是我们可以 appreciate 这个中国的古典诗歌，所以我两个礼拜之前我去了台湾，然后我发了一个这个我写的东西给他，大概就是叫做是其中有一句叫3月春芳翠洲行，君来求真应。浊音，然后 Prof 要跟我讲，他背负中国筹学之轮，只能够以荷塘钓海龟，没有垂音的情致，所以我后来把这个诗歌稍微修改了一下，所以这个应该是我作为他这个生日的一个最后一句话，叫做是梦里灞桥柳空门，晨茶云中说理问，茶是一种交通工具，出于庄子，所以 Happy Birthday Prof Thank you。
感谢姚教授非常精彩的发言，以及最后的对邱先生的一个感恩和祝福。但我们因为时间关系，也提一个问题，好吧？一个问题。
就是您做的这个，如果我们去做聚类那这个流行的格式是要求所有类只能是一样的，是吧？
对，
那么
什么叫流行的格式？
就是你的